Good morning, welcome to basic electronics class. In the last classes you studied op-amp. In that you studied applications of the op-amp, inverting, non-inverting amplifiers, summer or adder amplifier, subtractor or difference amplifier, integrator amplifier, differentiator, etc. The next topic is comparator using op-amp. So, before going to start the comparator circuit, let us consider what is comparator. The name indicates that it is a circuit, it performs comparing operation. What do you mean by comparing? So, we are comparing the two data. One is standard data, another one is incoming variable data. So, with respect to reference value or fixed value or standard data, we are going to compare the incoming data with the standard one or the reference one value. So, if you compare those two, then the possible combinations are, consider the two inputs V1 and V2. One input V1 is greater than V2. Otherwise, you will get V1 is lesser than V2 or V1 is equal to V2. So, these are the three possible combination of outputs from the comparator circuit. This operation is performed by with the help of the op-amps that in the comparator circuit. Okay? Before going to consider the comparator, we discuss the property called as saturation property. What is the saturation property? For the open loop op-amp, the gain is infinity. That is not good for practical application. If you provide the infinite gain, that is not good for the real time applications. So, consider this property for the practical op-amp with closed loop circuits. That is, the maximum output should be saturated output. That is, the output, maximum output, we can call this as maximum output is saturated value of the voltage, that is called as V saturation. V sat is nothing but the saturation voltage at the output side, that is equal to, this V saturation is equal to VCC or minus VEE, minus VEE. That is, the maximum output is obtained is equal to the supply voltages. A positive, if it is output is positive, means positive V saturation, that is plus 12 volts or plus 15 volts. If the output is negative saturation, means minus VEE, that is minus 12 volts or minus 15 volts, depending upon the input what you apply. The maximum output obtained in the op-amp is nothing but the saturated value, that is equal to V saturation, that is equal to VCC or minus VEE. Those are the two maximum value will obtain from the op-amp. Okay. Input voltage, I will consider some reference voltage. This is V reference. Consider this is the comparator circuit. In this we are applying two voltages. One is input voltage, which is applied to the inverting terminal. This one is reference voltage, standard voltage. With respect to this voltage, we are comparing the incoming input voltage, and that is applied at the non-inverting terminal. The input voltage is applied at the inverting terminal, means, so we can call this as inverting comparator. As usual, the RF value that is used to control the gain of the system. VO is the output, Vin is the input voltage, and V reference is the standard value. With respect to that, we are going to compare the value of the input with respect to reference voltage. Let us consider that the input voltage is a sine wave and reference voltage is a constant DC voltage, which is given as some plus 2 volts or 3 volts, whatever that. The input is AC, So it's going from 0 to maximum value, again going to 0, again negative value, again maximum, like this. It is oscillating between positive, 0, negative, negative, 0, positive, like that. This is the input voltage. Let us consider that this point I will call A. I will call this as point A, and this point as B, and this point as C, and this point as D, so on. From 0 to A, the input voltage is lesser than the reference voltage. Is it not? From 0 to A, input voltage is now increasing. This voltage is lesser than the reference voltage. That means input is applied at the negative terminal and reference voltage is applied at the positive terminal. The positive terminal voltage, that is V reference voltage, is larger. The V reference voltage is larger. That means the potential at non-inverting terminal is larger than the inverting terminal. Therefore, the output is what? Positive saturation. Positive value, because we are getting the more voltage at the non-inverting, which is the larger value. This larger value minus lesser value, you will get the what? The positive only. Therefore, from 0 to A, input voltage is lesser than the reference voltage. The output is at the positive saturation. Next, from the points A to B, that means here to here, the input voltage increasing with respect to reference voltage. The input voltage is larger than the reference voltage. Again, it becomes what? The input voltage is larger than the reference voltage. Therefore, the input voltage is larger means the voltage at the inverting terminal is larger compared to non-inverting terminal voltage. The potential or voltage at this point is larger means, which is negative. Negative is larger means we are getting the output as a negative inverted version. That is a negative output voltage. That is nothing but negative saturation. That is, from A to B, the output is at negative saturation. Again, consider from B to C, the points B to C. What happens from B to C? So, observe here, the input is going below the reference voltage. Here, the reference voltage is larger than the input voltage. Therefore, we can say that the input voltage is lesser than the reference voltage means input at the inverting terminal and reference voltage at the non-inverting terminal. The non-inverting terminal reference voltage is larger means you are getting the positive output voltage at the output terminal. Therefore, the output is at maximum, which is positive saturation. Again, from C to D, again what happens? The input voltage is increasing from the reference voltage. C to D, input voltage is larger, so which is at the inverting terminal, hence output is at the negative saturation. So, C to D, the output at the negative saturation. In this way, the comparator comparing two inputs, which is input voltage V in and V reference voltage. Therefore, it is giving the output voltage as input is greater than reference voltage or input is lesser than the reference voltage. So, this completes the module number 3, that is op-amps, operational amplifiers and its application. Next, I will start module 5. Module 5 name is Digital Electronics Fundamentals. So, in this module 5, you will study digital electronics fundamentals. What is analog? What is digital? What is the difference between the analog and digital? Analog means the sinusoidal input voltages or the output voltages. Those are called as the analog. That is, for example, a sine wave with respect to time, this is what? Input voltage. So, 0, pi, 2 pi. With respect to time, the information or voltage which varies continuously, that is nothing but the analog signals. That type of information or that type of signals are called as the analog signals. Even the noise is also an analog signal. Let us consider that, for example, noise. So, like this. So, this is also an analog, continuously varying signal. The information varies continuously, hence this is nothing but the analog signal. Example, sinusoidal wave, cosine wave, etc. Next is, we will consider digital. In digital, the information is not continuous. The voltage is not continuous. It is at a different time instant, we will get the different values of the amplitude or information. That is nothing but the digital signals. For example, this is the voltage, this is the time, at time t1, at time t2, etc., at time tn. So, the information is what? I will call this as 1. At t2, this is 2. At tn, it is 3, etc. This is nothing but the discontinuous. At different instant of time, you are getting the different values of the amplitude or the information strength. This is nothing but the digital. In this analog, the circuitry is complex and which is spurious to the noise, and the efficiency is less in the analog. So, due to these problems, the drawback of analog thing is, that is why we are going for the digital. In this digital process, accuracy increases, quality is increases, strength of the signal will be increases. Moreover, we can use with a low cost devices and which is less spurious to the noise. Efficiency increases in digital. So, these are the some differences between analog and digital. We are going for the analysis in the digital domain. In this digital electronics fundamentals, we will discuss first thing is number system. In digital electronics, we will discuss 4 types of number system. First one is binary number system. The second one is octal number system. Number 3 is decimal number system. Number 4th one is hexadecimal number systems. So, these are the 4 number systems: binary number system, octal number systems, decimal number systems, hexadecimal number systems. We will discuss in detail each and every one. The first one is binary number system. The name indicates that binary. What do you mean by binary? The binary means, bi means 2. Bi, B-I, bi means 2. In this number system, it has only 2 numbers to represent the number systems, or 0 and 1. It uses only 2 numbers. Observe here, 0 and 1. So, hence the name called as the binary number systems. In this binary number system, the radix or the base is equal to 2. That means a binary number system number x with radix 2, a number with radix or base 2 represents it is a binary number. If there is no radix, we cannot say that it is a binary number or any other number systems. If it is a radix or base is 2, then only we represent that as a binary number systems. For example, if you consider a number, binary number 1, 0, 1, 0, 1, means if you represent that in terms of 2, if you represent that as a 2, then it is a binary number. Without representation of 2 here, we cannot say this is a which number system. We cannot define this. Hence, we have to represent the base is very, very important. That is the radix is important. Here, similar to the decimal number system, we are considering from this side to this side. We are calling this as LSB, this is LSB, and this is the last one is MSB, and this one is LSB. Least significant bit and most significant bit. And the number 10101 I consider here with a base of 2. Here we are going to represent the positional value. Positional value of this number is, it is a whole number. There is no fraction here. Therefore, from here to here we are considering this is LSB and this is MSB. This number I taken here. The base is 2 only. Otherwise, we cannot say that it is a binary number. Now it is base is 2, hence we can call this as a binary number. The positional value of this is 2 power 0. This is 2 power 1. For this is 2 power 2. Positional value. And for this one is 2 power 3. For this one is 2 power 4. So on for the other numbers till 2 power n minus 1 for nth number. Because we are considering from 0 the nth number which ends at the n minus 1. Okay. So this is nothing but the representation of binary number system with respect to positional value. 2 power 0 means 1, 2 power 1 means 2, 2 power 2 means 4, 2 power 3 is 8, 2 power 4 is 16, so on. That is the positional value of this number. This number. This for the whole number. If you consider the fraction number, for example, 0.10110, if you consider with fraction value, you consider the numbers after the binary fraction or binary point, that is 10110, binary point. This is what we are representing the positional value after the binary point as 2 power minus 1, 2 power minus 2, 2 power minus 3, 2 power minus 4, 2 power minus 5. For the whole number, power is positive. For the fraction number, the power is negative after the binary point. So this 1, 2 power minus 1, this positional value, this positional value is 2 power minus 1, this positional value is 2 power minus 2, this positional value is 2 power minus 3, for this 2 power minus 4, for this 2 power minus 5, etc. This is the positional value of the binary number systems. This is the basic things. Now, in this number system, we can convert from one number system to the other number systems. For example, binary to decimal, binary to hexadecimal, binary to octal, that. Okay. We will discuss in detail after discussing all the number systems. Next number system is octal number system. Second one is octal number systems. The name octa means 8. In this number system, there are 8 numbers are used to represent the octal number systems. That is, octal number is 0, 1, 2, 3, 4, 5, 6, 7. Totally 8 numbers. 0, 1, 2, 3, 4, 5, 6, 7. 8 is not an octal number. Till 0 to 7 is nothing but the octal numbers. Okay. In this octal number system, the radix or the base is 8. For example, 1, 2, 3, 4, base 8. This is octal number. If you not represent the base as 8, we cannot say that which number system this number belongs to. If you represent the base is 8, then only it belongs to octal number. Here also, we are going to represent the positional value. For example, 1, 2, 3, 4, I consider. This is LSB or least significant bit. This is the most significant bit. For the whole numbers, the positional value is from right to left. In this one is least significant bit, hence this is nothing but 8 power 0. This one is 8 power 1. For 2, 8 power 2. For 1, 8 power 3. Like this, we are taking the positional value in terms of 8 powers or radix powers or base powers. Okay? This is for whole numbers. If you consider for the fraction number, so for example 0.12345, which is octal number, which is radix is 8, then so after the octal point we are considering from left to right side. That is, this radix is 8, this one is 8 power minus 1, this one is 8 power minus 2, this one is 8 power minus 3, 8 power minus 4, and this one is 8 power minus 5, etc. For the whole number, the power is positive. For the fraction number, it is negative. This is nothing but octal number systems. Next one is decimal number systems. Decimal number systems. The name indicates that it is a decimal, so which has 10 numbers to represent a decimal number systems, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 10 numbers which is present in the decimal number system. These are the 10 numbers which are present in decimal number system. But 10 is not a decimal number. Only 0 to 9 are the decimal numbers. Similar to binary octal number system, for the decimal number system, the radix or the base or radix is equal to 10, or we are representing this by D also, decimal D. That is 1, 2, 9, 4, 5. The base is 10 or D, which represents this number is decimal number. This number is decimal number. Here also the positional value is what? 10 powers. Similar to binary and octal, here also 10 powers. That is, I can say that here I will take the decimal number 1, 2, 9, 4, 5. This is the LSB for the whole number, this is the MSB, going from right to left. The radix power is, the radix is 10, the power is 10 power 0, 10 power 1, 10 power 2, 10 power 3, 10 power 4. So these are the radix or the positional value for the decimal whole number. For fraction number, consider for the fraction number. For example, 0.12347 decimal numbers. Then after the decimal point, the numbers are represented with for the positional value, it is nothing but 10 power minus values. That is, for 1 it is 10 power minus 1, for 2 the positional value is 10 power minus 2, for 3 10 power minus 3, for 4 10 power minus 4, for 7 10 power minus 5, like this. For 1 10 power minus 1, for 2 10 power minus 3, for 3 10 power minus 3, 4 10 power minus 4, and positional value of the 7 is nothing but the 10 power minus 5. So these are the positional values for the whole number and also fractional numbers. Next one is hexadecimal number system. The fourth one is hexadecimal number system. The name indicates that hexa. So there are hexa means there are 16. The value of hexa is 16. In this hexadecimal number system, there are 16 numbers are used to represent the hexadecimal numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Next is 10 is represented by A and 11 is represented by B and 12 is represented by C and 13 is represented by D and 14 is represented by E and 15 is represented by F. From 0 to F, totally 16 numbers are there. Our 16 numbers are used to represent the hexadecimal number systems. In this also, similar to binary, decimal, octal, etc., the positional values are the radix value. The radix value for the hexadecimal number is the base is 16 or we represent that by H, capital H. So the number represented with the base is 16 or H, which is nothing but the hexadecimal numbers. For example, consider 1, 3, 5, 7, A, B, C, H are 16. This number is hexadecimal number because a number with the base is 16 or H, which is nothing but the hexadecimal number. The positional value will represent the positional value for this, that is 1, 3, 5, 7, A, B, C, right. Here also whole number, it is from right to left. Right to left. The base is 16. The positional value of the C is 16 power 0. The base or the positional value of the B is 16 power 1. The positional value of the A is 16 power 2. Positional value of the 7 is 16 power 3. For 5, it is 16 power 4. For 3, positional value of the 3 is at 16 power 5. And for 1 is 16 power 6. So this is nothing but the positional value of the hexadecimal number with whole number. If you consider a fraction number, if you are considering the fraction number, that is 0.35127 or 1245A. Okay. Consider that this is the fraction value for the hexadecimal number. Hence we can write, I will take this here. So after the hexadecimal point, the positional values are minus 16 power minus 1, 16 power minus 2, 16 power minus minus minus. Okay. That is 3, 5, 1, 3, 5, 1, 2, 4, 5, A. 3, 5, 1, 2, 4, 5, A. So after the hexadecimal point, we are considered from left to right side. Okay, that is 3 means 16 power minus 1. The positional value of 5 is 16 power minus 2. This one is 16 power minus 3. This one is 16 power minus 4. 16 power minus 5. 16 power minus 6. 16 power minus 7. So on, etc. Those are the positional value after the hexadecimal point. After the hexadecimal point. So these are the basic concepts of different number system. Binary number system, octal number system, hexadecimal number system, decimal number systems. Okay. I will continue in the next class. Thank you.